Section 4. Working with PySpark and MongoDB. In this section, we're going to look at the fundamental concepts of Spark. Spark has a particular way of thinking about data and processing, so it's important to understand these concepts underlying it so we can write effective Spark code. That includes looking at the data structures in Spark. We'll also introduce pySpark as the Python API for the Spark library, before finally looking at how we can use MongoDB together with pySpark. What is Spark and when do we need it? In this video, we're going to ask what is Spark useful for? We're going to review the key concepts in Spark, and then finally look at how to install Spark so you can have Spark up and running on your computer. That will allow you to follow through the examples and also to extend those examples to start to build your own Spark processing pipelines. In one sentence, Spark is the most popular software framework for processing large datasets. We can ask, when should I use Spark? And there are two parts to this. The first is the situation when the data you wish to process is too big to fit in the memory of your machine. Let's say you have 16 gigabytes of memory, but your dataset is 50 gigabytes. It's not possible to load that data directly into your memory on one machine. While you could simply buy a new machine with enough RAM to load it in, a better approach is to consider the memory of several machines combined together. Well, that's preferable because that way you can scale up your processing by adding new machines incrementally rather than having to buy a new machine each time. Spark helps you to distribute that data across several machines in a way that makes sense. Analogously, if your processing and analyzing is too intensive, let's say you have a pipeline that might take several days or weeks to run, if that's not practical for you, you can use Spark to break up the processing across several machines so each piece can be processed in parallel, thereby bringing down the total running time of your calculation. And Spark helps you share that processing burden across many machines. Spark is part of the Apache repository of software, and it is based on the Hadoop implementation, which is written in Java, of the MapReduce algorithm. There may be lots of phrases in there that you don't fully understand, but don't worry too much about that. I would say if you are interested in the MapReduce algorithm, then it's worth going back to the original Google paper to read a little bit more about it, because it's very easy to read and it's a very powerful concept that underlies a lot of big data processing. We can understand this a bit better by looking at this figure. So here we have a problem data set which we would like to run some kind of operation on. So the first step is if we follow the red arrows, is to break down that data into n pieces and send one piece to each of n worker nodes. The number of nodes is arbitrary, but it should surely be greater than 1. The more the number of nodes you have, the smaller the chunk that each gets, the quicker that all of the data can be processed in general, but there is more overhead for communicating between processes. So each worker node has its small chunk of the data, and it does some operation on that data independent of the other pieces. Once it's finished, it sends the data back to the master node, that's the blue arrows, and the master node will perform some kind of reduce operation, which takes together all of the individual results on each chunk and combines them together into one set of solution data, which is the piece on the bottom left here. The most obvious example, rather the most commonly used example of the MapReduce algorithm, is to count the frequency that words appear in a large set of documents. Now let's imagine that the problem data is a big set of documents. And what we would do then in the map step is to break those documents into n chunks and send one chunk to each worker node. Each worker node would look at the documents it has received, and it will count the frequency of the words appearing in those documents it's been assigned. And note that each node can do that independently of each other node. There will be some operations that cannot be broken down in such a simple way, but many can. Once each node has counted the frequency of its documents, the results are sent back to the master node. The master node then takes those individual results from each node, combines it together to get the total word counts across all the documents, and the result of that is put into the solution data. Other features that are worth noting about Spark. Like PyMongo, MongoDB, and Python, it is open source, so you are able to use it without any restrictions. I should add that if you want to use Spark in a sort of hosted environment with support, you are able to do that for a cost. As we've mentioned, Spark allows data and processing to be parallelized and distributed across many machines. It also has clean APIs in Scala, Python, Java, and R. So that means we can access Spark across all of these different languages. Perhaps the most appealing part of Spark is the growing libraries for doing machine learning, graph and network processing, and analyzing streaming data. These libraries are growing very quickly, and there are very frequent new releases of Spark, so it's a very exciting time to learn about this framework. There are a few key concepts to Spark that I'm going to just briefly describe here. They'll become a bit clearer as we work through some code, but I just want to put them on your radar now. The first is lazy evaluation. What this means is that Spark will delay evaluating anything until the last minute. Let's say I have a dataset and I apply one operation followed by a second, followed by a third. None of those operations will actually be implemented until I take some action which asks for the result of that pipeline of 3 operations. At that moment, Spark will look at the operations that have been effectively queued up, and it will figure out in a very, very smart way, how can I do those steps optimally? It may be that the result of step 3 influences step 1 in a way that you can do it in a smart way and cut down the overall processing burden. We'll talk a bit more about transformations and actions and see if we can get a bit closer to that idea, but just bear in mind lazy evaluation for now. Spark is very strongly influenced by functional programming. If you're familiar with functional programming, that's great. If you're not, don't worry about it. What this basically means is it's a style of programming where your data or your system does not have a state. You rather perform some operations and get back some result. As a result of that, you cannot change any of the data structures in Spark. They are immutable. If you want to perform some operation on a data structure, then you will return back another data structure. You cannot amend that original one. Resilience is also fundamental to Spark in the same way that MongoDB splits across many machines and is resilient to any failure in any of those individual machines. Spark will automatically recover if one of the machines breaks down. That might not be such a big deal for small operations, but if you have hundreds of machines running for days and days at a time, some up and running app, you want to have your system able to quickly recover from any individual failure. Finally, Spark data structures are unindexed. We discussed the advantages of indexing with MongoDB, but basically from the complications that arise from sharing that data across many machines, Spark data structures don't offer indexing. The Spark is a complex framework. It is also complex because it has a very deep stack. So it's written fundamentally in Java. The original API is through Scala, and then we kind of have our Python layer through pySpark. So quite often the error messages are a bit difficult to interpret, and the documentation is maybe not as good as we would like. That said, this situation has improved a lot in the last couple of years, particularly around installation. So you should have not such a difficult time installing Spark. The basic steps are you will need a Java installation. At the time of writing, you must have at least version 8, but version 9 is not supported. That may have changed by the time you come to set up your system, but I would recommend Java 8 for now. You should go and grab the latest Spark installation from the Spark homepage, and grab that and put it in a sensible place, either within your home directory or somewhere else in your system libraries. And then finally, you want to install pySpark. And that allows you basically to easily connect to the Spark server through Python and through Jupyter Notebooks. Thankfully, Conda has added pySpark to its repositories, so if you use the Conda installer, you should be able to easily set up pySpark. It's very easy to know if that's all been successful. You should be able to run pySpark on your terminal window, open up a Jupyter notebook, and in your Jupyter notebook, you should, for free, be given the variable sc, which stands for Spark Context. And that Spark Context is basically the gateway into the Spark server. If you evaluate sc, you should get that should run without any errors and give you back some information about your Spark context and your Spark server.